Today we are going to learn about optimizing KNN for big data applications. We will explore how to enhance the k-nearest neighbors algorithm for handling large datasets efficiently. By the end, you'll know how to manage KNN computations effectively and gain essential skills for processing big data applications. Welcome to the world of k-nearest neighbors, commonly known as a simple yet powerful machine learning algorithm. KNN is used for classification and regression tasks, where it identifies the k closest data points to make predictions. However, as we step into the realm of big data, KNN faces significant challenges. The algorithm's computation time increases dramatically as the dataset size grows, making it less efficient. In today's session, we'll delve into these challenges and learn how optimizing KNN is becoming essential. As data continues to grow exponentially, learning how to process it efficiently is crucial for any data scientist or engineer.
As datasets grow, the time complexity of KNN becomes a significant bottleneck. Consider that for every prediction, KNN must compute the distance to each data point, which becomes increasingly cumbersome with larger datasets. This not only impacts computation time but also memory usage, as more data requires more storage. Performance suffers, and without optimization, KNN becomes impractical for real-time applications. Understanding these impacts is crucial for those working with large-scale data. By identifying these challenges, we can focus on finding innovative solutions, ensuring that KNN remains a viable option in the world of big data.
To optimize KNN for large datasets, we turn to efficient data structures like KD trees and ball trees. KD trees divide the data space into partitions, allowing for faster nearest neighbor searches by reducing the number of calculations needed. Ball trees, on the other hand, use hyperspheres to encapsulate data points, which can be more efficient in higher dimensions. Both structures are designed to enhance KNN's performance by minimizing the number of distance calculations. By implementing these data structures, we can significantly improve the speed and efficiency of KNN, making it more scalable for big data applications. Dimensionality reduction is a critical strategy for optimizing KNN, especially in datasets with a high number of features. Principal component analysis, PCA, is a widely used technique that reduces dimensionality by transforming data into a set of linearly uncorrelated variables called principal components. This reduces the number of features while retaining most of the dataset's variance. t-SNE, on the other hand, is a technique that excels in visualizing high-dimensional data by reducing it to 2 or 3 dimensions, preserving local structure. Both techniques cut down the computational complexity of KNN, making it more efficient and faster, which is essential for handling big data. Parallel processing is a game-changer for optimizing KNN in big data environments. By distributing computations across multiple processors or cores, we can significantly reduce the time needed for distance calculations. Techniques such as data parallelism and task parallelism can be employed to split tasks into smaller, manageable parts. Leveraging modern hardware, such as GPUs, further enhances scalability, allowing KNN to handle massive datasets efficiently. This approach not only boosts performance but also ensures that KNN remains a viable algorithm even as data scales upwards.
The choice of K in KNN is crucial, as it directly affects both the accuracy and computational efficiency of the algorithm. For large datasets, selecting the right K becomes even more challenging. A small k might lead to overfitting, while a large k can result in underfitting. To find the optimal k, one must balance between performance and efficiency, often using techniques such as cross-validation. By adapting the value of k to the dataset size and nature, we can ensure that KNN maintains its predictive power while being computationally feasible for big data applications. Let's explore a real-world case study where KNN was deployed in a big data environment. In this scenario, a large retail company used KNN for customer segmentation. Initially, the algorithm struggled with the dataset size, leading to slow processing times. By employing optimizations such as KD trees and parallel processing, and carefully selecting the right K, the company managed to enhance KNN's performance significantly. These adjustments led to faster computations and improved accuracy, demonstrating the power of optimization techniques. This case study highlights the practical implications of optimizing KNN and the tangible benefits it can bring in a big data setting.
Implementing KNN for big data requires careful consideration and adherence to best practices. Begin by ensuring data quality, as clean data leads to better performance. Avoid common pitfalls such as setting an inappropriate K value or neglecting dimensionality reduction. Optimizing parameter settings, like choosing the right data structures, can make a significant difference. Keep in mind that continuous improvement and testing are essential for maintaining efficiency. By following these practical tips, you can minimize errors and maximize the effectiveness of KNN in any large-scale application.
As big data continues to evolve, so does the role of KNN in this dynamic landscape. Emerging trends such as the integration of KNN with AI and machine learning open new possibilities for enhanced data analysis. Optimization techniques are advancing, providing more opportunities to improve KNN's efficiency and applicability. However, challenges remain, particularly in adapting KNN to handle increasingly complex datasets. By staying informed about these trends and innovations, we can proactively address potential issues and harness the full potential of KNN in future big data applications. In conclusion, optimizing KNN for big data applications is not just a technical necessity but a strategic imperative. We've explored various strategies, from using efficient data structures and dimensionality reduction techniques to parallel processing and choosing the right K. These optimizations are crucial for maintaining KNN's relevance in the era of big data. As we move forward, it's important to continue learning and applying these skills to real-world challenges. The future of KNN in big data is promising, and by staying informed and adaptable, we can unlock its full potential.